Uh, so today, I'm Adam Freese. I'm a postdoc at the Center for Nuclear Femtography, and I'm going to talk to you today about mechanical properties of the proton. The Center for Nuclear Femtography is a center at Jefferson Lab, which is a joint effort in theory and experiment, funded by the state of Virginia to facilitate the application of, basically theory, computing, data science, to studying the structure of hadrons. We're focused primarily on the spatial structure of hadrons. That includes generalized parton distributions, which I just realized I didn't have my mic on. You can all hear me okay though, right?
Yeah.
All right. So we're focused primarily on the spatial structure of hadrons, which includes generalized parton distributions, which I won't talk about today, but GTU will give lectures about on Friday, so definitely attend those. High energy various electron photonuclear nuclear reactions, which probe the GPDs, and the thing that I'm going to focus on in this talk, the mechanical properties of hadrons, which technically speaking are accessed through the generalized parton distribution. So the GPDs are still very important. They're kind of there in the background. And here's our website. All the pink text in these slides are clickable links if you want to download them and follow up on any references I cite for images. The Center for Nuclear Femtography currently consists of 4 people here at JLab. There's Latifa, our director, David, our associate director, and then Krishna and I are the 2 postdocs working for CNF currently. What the CNF does, besides employ postdocs, is we hold various sorts of events. We host a seminar series. The seminars usually take place in person at JLab, but they're always streamed on Zoom. If you want to be made aware of when a lecture is happening, you can sign up for the mailing list at this link. Email me and I'll let you know. We also organize lecture series and various sorts of summer schools. A couple of years ago, we had the first International School of Hadron Femtography, which was jointly organized with the Quark Gluon Tomography Topical Collaboration. That was very exciting. There were a lot of excellent lectures there. And together with the QGT collaboration, we're planning another summer school for 2027. However, this summer, we're going to have a standalone lecture series by Cedric Lorset, which should be excellent. We also partially supported, I'm not sure you'd pronounce it, CNUGS, CNUGS, how are you all pronouncing that? And if you want to read it, this is the abstract for Cedric's lecture series. He's an absolutely wonderful lecturer, and there's going to be a lot of overlap with what I talk about today. He's a better lecturer than me, so if you can, definitely attend these lectures. So the kind of the main teaser for what I want to talk about today and the follow-up lectures on Wednesday is the pressure in the proton. Of course, that's one of many things that we mean by mechanical properties, but it's probably the thing that gets talked about the most. Empirical extractions of the pressure in the proton are happening here at JLab. We've even gotten a few Nature papers out of them in 2018 and 2023. There have been some very recent measurements just this year, haven't even made it through peer review yet, but have appeared on the archive from both Hole C here and the class collaboration measuring the pressure in the proton. Although we have these measurements happening, the interpretations of what we're measuring are still controversial. When we talk about pressure in the proton, which is not like a classical system that you can describe thermodynamically, what do we mean by pressure? What do we even actually learn by measuring it? And is relativity properly incorporated into the pictures that we're drawing here? All of these things are controversial. This is not settled science. There's a lot of fairly heated arguments happening in the literature. I'm going to give my perspective on all of this, but reasonable people can disagree. So if you hear another lecture or attend a seminar or something where people are saying things that contradict me, then, well, that's kind of normal for cutting edge science. Just listen to everyone, put pen to paper, do your own calculations, and try to determine for yourself who's right. So there are 4 controversies that I'm going to touch on in this series of lectures. One of them concerns the proton mass. These controversies involve things like how much of the proton's mass is due to the masses of the quarks, say to the Higgs mechanism, versus how much is dynamically generated by the interactions between quarks and gluons. There are a couple of different answers floating around. Can any of the proton's mass be called anomalous? There's some people who say yes, some people who say no. That's not settled, and the controversy gets pretty heated sometimes. Next, there's the controversy about proton spin. To spoil it a little bit, I'm not going to talk very much about that because I'm less an expert in that than the other topics. But I will touch on the questions of how much of the spin is carried by the quarks, how much by the gluons, and how much of it is orbital motion as opposed to the intrinsic motion of these intrinsic spin of these particles. Then I'll talk about the proton pressure. These last two sections are going to be much more extended than the first two. One of the questions that actually is being debated right now is it actually even meaningful to talk about proton pressure? I'm going to say yes, and I'm going to make an argument for it, but that is a open question. And even if we measure this pressure profile, do we actually learn anything about QCD forces and how they operate from it? Or is it just kind of, you get a number, you can plot it, and that's it? The last thing I'm going to touch on, which probably will be the most extended section because it's something I've been involved the most in the debates about, how exactly are you to define densities of relativistic quantum systems? There are different answers to this, and people fiercely disagree with each other. But something these controversies will have in common that will be the thread uniting these lectures is the energy momentum tensor. So that will be the first topic I go over. So the energy momentum tensor is a rank 2 tensor. You can kind of think of it as a 4x4 matrix characterizing the density and flow of energy and momentum. Its components can be interpreted as an energy density, momentum densities, energy flux densities, and momentum flux densities, or the stress tensor. How you get it? There are multiple different ways of deriving an energy momentum tensor in a quantum field theory. The first one you probably are familiar with from the textbook is through Noether's theorems, more specifically through her first theorem. Noether's theorems tell you that symmetries entail conservation laws. Spatial translation symmetry gives you momentum conservation. Time translation symmetry gives you energy conservation. And the conserved current you get from these symmetries can be used to define the energy and momentum densities. So I have a few kind of step-by-step derivations in this slide. You can follow along if you want to. You can ignore it if you're not interested. But I think it's worth putting pen to paper and doing all of these derivations at least once. So with her first theorem and space-time translation symmetry, the idea is to say that your Lagrangian depends on space and time only through the fields. So derivative of the Lagrangian, you use the chain rule, depends on how it depends on the field, how it depends on the field's derivative. And in any realistic field theory, that's the end of it. If you had that the Lagrangian depended on the second derivative, you'd have more terms. You take this Poppleton here, and you use the product rule in reverse. You write a total derivative of this quantity here, minus you flip this derivative to act on this term instead. You can then gather the terms that have a partial nu psi on the outside to one side, and everything else is a derivative on the other side. And then you can say, well, this quantity here is 0 if the Euler-Lagrange equations are satisfied. This is the Euler-Lagrange equations. Then because this is 0 when the equations of motion are satisfied, this purple term has to be conserved. So that's how you get the canonical energy momentum tensor. It's conserved only if the Euler-Lagrange equations are satisfied, which is actually important. Noether referred to conservation laws like this as proper conservation laws. They're conservation laws that can be violated if your equations of motion aren't true, which can happen if there are degrees of freedom you're not accounting for. In other words, you can have energy and momentum transferred to other degrees of freedom. So you have this continuity equation. You have this divergence of this EMT is 0. You can rewrite this in an integral form like this. And this gives you the physical interpretation that energy and momentum can change in some compact region of space only by flowing into or out of the region through its boundary. It's for this reason that these lower components here are interpreted as energy fluxes and momentum fluxes. Now, there is a problem with the canonical EMT, and you might be familiar with this from your field theory classes. Well, if you have a gauge theory, then your canonical EMT is not gauge invariant. In fact, right here is the canonical energy momentum tensor for quantum chromodynamics. You have this term right here is not gauge invariant, this is not gauge invariant, which means that the energy and momentum densities depend on the gauge you choose, which should not be physical. It's supposed to be a redundant degree of freedom. So this is a fatal flaw in the canonical EMT, is not an acceptable physical quantity. Okay, so this is another one of these step-by-step derivations I have. If you read Zixin and Zuber, for instance, they'll work this out for the free electromagnetic field, the Maxwell-Lagrangian. The relevant derivatives in your canonical EMT, which is defined this way, are you take the derivative of Lagrangian with respect to the derivative of your 4 potential. You can use the fact that this is squared, get to this on the outside that, write it out in terms of your field derivatives. You get a couple of Kronecker deltas, and you use the fact that this guy here is antisymmetric, and you get minus F mu rho if the indices are mu and rho down here. And if you plug that down here, this is what you get. And you have this term here, which is not gauge invariant. You can change it by just doing a gauge transformation. It's worth working this out for QCD2. I'm not going to do that step by step because there are a lot of terms. You can pretend it's a homework problem if you want to pretend you're doing homework for this summer workshop. All right, so we have this canonical EMT that's physically not acceptable, even in something as simple as the free electromagnetic field. The way that this is conventionally dealt with is what's called the Bell-Infante improvement procedure. You create this tensor that is trivially conserved. Noether would call this an improperly conserved quantity. So you have here a quantity, this lambda mu nu rho, which is antisymmetric under exchange of the indices mu and rho. This is a Levi-Civita symbol. And of course, this is your field strength tensor. So if you take the divergence with respect to the rho index, then taking another divergence with respect to the mu index gives you something that's trivially 0. So you can add something that's trivially conserved to your canonical EMT, and you will again get something that is conserved only when the Euler-Lagrange equations are satisfied. You can also use the Euler-Lagrange equations. I didn't do a step-by-step derivation here, but you can do that in your spare time if you would like. And you can rewrite the canonical EMT plus this trivially conserved quantity in this form, which is now gauge invariant. It depends only on the gauge covariant derivative and the field strength tensor. The procedure works, but it's kind of ad hoc, and because of that, I find it unsatisfying, and a small minority of physicists also find it kind of unsatisfying. So there is a way that you can just, from Noether's theorems, directly get a gauge invariant EMT. It's to use local space-time translations instead of global ones. Basically meaning instead of translating all of space by a constant amount or time by a constant amount, you kind of deform space. Each point in space you move by a different amount. So you use the rules for general coordinate transformations for your fields, which you can find in a general relativity textbook, for instance. Your scalar field, new field in terms of new argument is equal to old field in terms of old argument. And for something with a index, you have these transformation matrices in front of them as well. Now, new field, new argument isn't the same as new field with old argument. We define the so-called Eulerian change as new field with respect to old argument. For what this means, you can imagine you move everything in space by a different amount, so horizontally in a plot of x versus a function. Some of your changes might be bigger, some of your changes might be in the opposite direction. You then take your new function and subtract the old function. So now you look at the vertical differences. And that's how you get this Eulerian change. So I'm going to go through a couple of worked examples of this for scalar and then for vector fields. You have your trivial change in your scalar field. And this is your rule for how space-time is transformed in a space-time dependent way. The action changes only through the fields under this assumption. So we're not transforming the metric tensor or anything like that. The first thing you want to do is put in the old field in terms of the new field. This has a minus here, so we have a plus here. Next, we're going to expand this to only linear order in xi. So you end up getting the leading order term plus the derivative multiplied by xi. The argument in here doesn't matter because new or old space-time coordinates, you're going to get a difference of order xi, and we're already multiplying that by xi. So that would be order xi squared. You can do the same thing over here. And now you note that, well, these are the same. So you drop them. And for the change in derivative, you now have a derivative multiplying xi, and oh, that should be the derivative of phi right here. Looks like I have a little typo. Oh, the typo's fixed in the next step. You apply the product rule, and now you have two terms on this side. So with these changes, you can plug in the change in your Lagrangian by using the chain rule. The changes only occur through changes in the field. And then you substitute in these two expressions, and you get three terms like this. From here, you gather these terms with xi on the outside, and you say that this is the derivative of the Lagrangian by doing the chain rule in reverse. And you have kind of this extra term here with a derivative acting on xi. For that, you do integration by parts. An assumption that we make in applying this is that the local space-time translation has compact support. So we only translate things within some small region of space-time and not all of space-time. So we can drop surface terms. Yeah, this is the combining things. And by dropping surface terms, we only get now the derivative acting on everything else instead of xi with a minus here. We can pull out the xi and the derivative. And then we say, if the change in the action is 0, then this quantity in here has to be conserved. Now, it's not immediately obvious that a local space-time translation, this deformation of space-time, should result in the action being unchanged. And in general, it doesn't. However, it turns out that the action is invariant under these changes if and only if the Euler-Lagrange equations are satisfied. So this is one of those, what Noether would call a proper conservation law. This quantity is conserved only if this change in the action is 0. For the more general case, say you have some degrees of freedom you haven't accounted for, you can think of this as affecting some sort of change in the action, a way your theory responds to deformations in space-time, which will be really important for a later lecture on pressure. So how about vector fields? The story's kind of the same. You have a rule for transforming the 4 potential, and because it's a rank 2 covariant tensor, a rule for transforming the field strength tensor. The fact that the Lagrangian depends on the field strength tensor and only depends on the derivative of the 4 potential through the field strength tensor is actually really important for this working out. So you can follow the same series of steps. You replace x with x prime plus xi. You expand to linear order in xi. You then write this in terms of this transformation rule, which will give you basically a 0th order term two linear terms, and you'll have a second order term in xi, which we're dropping since we're only expanding to linear order. And if you contract all the indices and multiply it out, then you end up getting a transformation in your 4 potential that looks pretty much exactly like the transformation in the derivative of the scalar field. Then for the field strength tensor, you have 2 extra terms instead of 1 extra term. So you have these rules, and if the action changes only through changes to the fields, you do the chain rule as before. You substitute in these expressions. You gather the terms that have a xi nu and not a derivative of xi in them, and you note that applying the chain rule in reverse, this is the derivative of the Lagrangian. For these extra terms, we would like to do integration by parts again, but we have kind of the inconvenience that this has a rho instead of a mu. But then we can use the fact that mu and rho are dummy indices that are summed over, and and then just swap them. They're dummy indices. We can relabel them however we want. And okay, this is nice. We now have a partial mu. This is a rho. I mean, these are opposite, mu rho, rho mu, but these are opposite too, nu rho, rho nu. And the field strength tensor is antisymmetric, so you can do both those swaps at once. And these 2 terms are the same, you get a factor 2. Now you do integration by parts. Now you gather terms like before, and you end up with something that is conserved if and only if the action is invariant, which occurs if and only if the Euler-Lagrange equations are satisfied. So this would be our energy momentum tensor if we use local space-time translations as our symmetry group. So does this give us a different answer than the canonical EMT? Well, our relevant derivative is now with respect to the field strength tensor. So it's a little bit easier. We get 2 times pull one of these out. This derivative is going to just involve these Kronecker deltas, and we just end up with this. We get a factor 2, which we saw before. We plug this in. We get this. We swap this nu and this rho just because I think it looks prettier if you do, and we get this expression. In fact, it's exactly the same as the Bell'Infante EMT for electromagnetism. So by using these local space-time translations instead of global space-time translations with Noether's theorems, you get the Bell'Infante EMT automatically without having to do any sort of ad hoc improvement procedure, which I think is pretty elegant. It's worth doing this for QCD too, but there are a lot more terms, especially if you're doing quantum chromodynamics and you have all these gauge fixing terms and these ghost terms. It's a lot. It's a fun homework problem though. Now there is one caveat that actually will make the EMT we get from this procedure different from the Bell'Infante EMT, which is that spinors, instead of having their components mix up under these local translations, just transform like scalar fields or like a collection of scalar fields. Dirac spinor has 4 components, so it transforms like 4 independent scalar fields. Why don't they mix up? It's actually very technical. When you do a Lorentz transformation or a rotation or something like this, you have this double cover of your Lorentz group or your rotation group. But you don't have a double cover, or at least there's not a finite linear double cover of your collection of general coordinate transformations. There's technically a nonlinear double cover, which is really complicated. It's called the metalinear group, and there's hardly any literature about it. But it's extremely messy and almost never used. In practice, most physicists treat spinors as transforming like scalars under general coordinate transformations, and they have this fairly complicated and elaborate framework called the tetrad or the Vierbein formalism to deal with the spinor nature of the fields. The original proof that this doesn't work out is in Cartan's theory of spinors. I have an elementary proof in the appendix of this paper that should be followable just using the raising and lowering operators of the angular momentum algebra. There are definitely more elegant proofs out there, but I couldn't remember where I had read them when I was preparing these slides. I might edit the slides to add more references if I can remember where the more elegant proofs are. Anyway, in the end, you get from this procedure a energy momentum tensor, which is gauge invariant, but whenever you have fermions such as quarks, is not symmetric under exchange of its indices. In principle, because the Bell-Infante improvement was kind of ad hoc, we could have defined our superpotential differently. In fact, we could use this very minimal superpotential instead, and we would get this EMT from it, which is not symmetrized. It's in fact, this is the minimal choice needed to maintain gauge invariance. So Cedric Lorset, whose lectures will be this summer, definitely worth watching if you can, is a big advocate of this kinetic EMT, as he calls it. And his preferred method of derivation is the standard first theorem plus improvement using this minimal superpotential. So what does the symmetric versus asymmetric mean? Well, if we want to start talking about how we would calculate and describe the energy momentum tensor of a hadron, we do this through form factors. I'm sure you all are familiar with electromagnetic form factors or elastic form factors. Mechanical form factors are defined analogously. You take your EMT operator, you sandwich it between momentum kets, and you write out the most general possible structure you can that's compatible with the quantum numbers and the symmetries of your operator. In principle, you get up to 5 form factors. One of them is hidden by this little window, which actually makes me a little sad because the one that's being hidden is called the C-bar form factor. It's my favorite form factor, and I like to complain about how it's overlooked. And it looks like even Zoom conspired to overlook it. Now, funny thing about C-bar. Okay, so we have these 5 form factors, A, D, J, S, and C-bar. The S1 is the anti-symmetric part, and the rest of these are from the symmetric part of the EMT. I'm going to skip this slide, it's not too important, or I'll go back to it. I would actually like to talk about the sum rules first. Now C-bar, the reason it's overlooked is if you sum over all constituents, local momentum conservation means that C-bar has to vanish. The reason for this is that at the level of form factors, taking the divergence amounts to contracting delta mu with this. Now P mu dot delta mu, it's pretty straightforward to prove, is already 0, so this drops out. This is already delta mu, you get a delta squared minus a delta squared. This is 0. This will drop out. This will drop out. This will be the only thing that survives. So if you sum over all constituents in a system, local momentum conservation requires that C-bar vanishes. However, if you look at a subsystem, momentum doesn't have to be conserved. It can be transferred between subsystems. It can be transferred between constituents. So C-bar tells you something about how momentum is being sloshed around between parts in your system. You also have these other sum rules. Specifically at 0 momentum transfer, your A's have to add up to 1. This is related to the momentum sum rule for parton distributions. And you have an angular momentum distribution. Your J's are related to angular momentum. This is called the G sum rule because Shandong Ji discovered it in this paper. Now, C-bar, it's 0 for the entire system, but for subsystems, it can be non-zero. And in fact, if you take the Fourier transform of this and the divergence of the Fourier transform, this tells you about forces that a subsystem is feeling from the other constituents. This was talked about by Maxime Polyakov in this paper. All right, so I do want to say that mechanical form factors is a little bit of idiosyncratic jargon. Some other people are using it, but it's not the favored jargon. Most people refer to these form factors as gravitational form factors in a way that makes it sound like you're doing something really edgy, I guess. And it is technically correct because the energy momentum tensor is the source of gravitation in general relativity. So that's fine. but I feel like it kind of confuses people or misleads them sometimes because we're not describing gravitational forces between the quarks and gluons. We're not using gravitation to measure them. We're not really studying anything about gravity at all. We're studying the mechanical properties, and it just so happens that the object we're studying is also the source of gravitation. So I feel like the gravitational part isn't the most important part of these quantities. EMT form factors is also widely used, and that makes sense because they're form factors of the energy momentum tensor. But a lot of literature actually calls this the stress energy tensor instead. I've actually referred to it as merely the energy tensor a few times in this lecture already. So I like to call it the mechanical form factors because we're describing mechanical properties. That's the main thing we're trying to learn from them. The downside is it's not in widespread use. So you should know that I'm using a bit of a peculiar phraseology here. Now, how do you get the mechanical form factors? I'm actually not really going to go into this. There are currently two ways. You can use lattice QCD, which are probably the most accurate, precise, and trustworthy extractions in existence right now. The group of Daniel Hackett, Dimitra Pevku, and Fialo Shanahan have done really good work on this. There are also some early empirical extractions. They tend to be pretty model dependent, but there are some empirical extractions primarily coming from JLab. The Hatta et al. Is actually a feasibility study rather than an extraction itself, but Shintanyan et al. Is an empirical extraction. And if you want to learn more about the formalism, you can look at the slides from this mini workshop the CNF organized recently. And if you want to learn more about GPDs and the reactions that are sensitive to the EMT, I believe Jita's talk on Friday will be very enlightening. All right, so what are the controversies here? Well, there are four. Again, I kind of said this earlier. There's open questions about the proton mass, which is related to this component of the EMT, the energy density, since mass is energy of a system that's at rest. There are questions regarding proton spin. They're related to these momentum densities. There are questions related to the meaning of proton pressure. At a more fundamental level, you could call it momentum flux densities, but can the momentum flux densities be interpreted as stresses and pressures? That's this submatrix, 3x3 submatrix of the EMT. I've kind of left the poor little energy flux densities out. They're really important for some other important topics in hadron physics. Energy correlators are related to these, but I basically know nothing about them, so I'm not going to comment on them. And lastly, all components are related to how do you define densities of relativistic quantum systems. So I'm going to start off by talking about the proton mass. I guess this would be a good time for a short break to take any questions.
Do you have any questions so far?
If not, I can continue. By the way, what time is this lecture going until?
2:30.
Okay. Well, I think I can at least make a bit of a dent in the mass one, maybe not finish it. All right. So I alluded to earlier that the way that I'm going to tackle proton mass is to say that by mass, I mean proton energy in the rest frame. The energy density is this component T00 of the energy momentum tensor. And if you look at either the Belinfante or the kinetic energy momentum tensor, you get the same answer for this component because, of course, T00 anti-symmetric part isn't going to contribute. So there are multiple sorts of breakdowns, but the breakdown that I think makes the most sense is you break this down into quark masses. This is actually nice because it is renormalization group invariant. You have a quark kinetic energy and a gluon energy. These are both gauge invariant. Unfortunately, they're not renormalization group invariant, so depending on how you do renormalization, you're going to shuffle some strength between those. And they'll also evolve with your renormalization scale. Something tricky whenever you deal with a field theory. All right, so how do you get a mass out of this? Well, let's start with the basic thing. We consider our proton. We consider the expectation value of the Hamiltonian. That will be the average energy. And in the end, we're going to take our proton to rest. So this average energy just becomes the proton mass. Well, the energy is just the integral over space of the energy density. Simple enough. We then throw some completeness relations in. Sum over all possible momentum and spin states of the proton on both sides. The next thing we're going to do is we're going to take the x dependence and we're going to write this in terms of generators of translations. Generators of translations can now act on the respective momentum kets. This will be P prime, this will be P. And now we do a variable change. We define a big P as an average momentum between the initial and final state, and a delta as the momentum transfer in green and purple. And we also move around all of our EP primes, our P primes, our Ps, already combine this into a delta. And I've already anticipated the next step. In blue here, we now have all of the x dependence. And this just becomes a Dirac delta. The Dirac delta sets your momentum transfer to 0. You can do this delta integral, and you're left with an integral only over big P now. You also have a sum over 2 different spins. This is something that I've kind of skipped over the details here, but you can go back a few slides to the way that the mechanical form factor breakdown is written, and you can find that this only survives when S and S prime are equal. So you can write it as a sum only over S. And now, finally, you can take your wave packet here going to a 0 momentum plane wave, in which case this just becomes your operator between 2 kets of a 0 momentum plane wave. So you have your masses equal to this matrix element. I'm using this double bracket here to mean an average at the 0 momentum limit divided by 2m. And in this way, you get that the mass decomposition can be written as these 0 momentum wave packet limits of each of these operators. And you can refer to these references for more details. Oh, yeah.
Does it also work for like deltas and things like that, like just like these resonances, or is there
I think, yeah.
Good.
As long as you assume that they are genuine one particle states, so that this isn't actually a completeness relation. I'm not sure to what extent the fact that they're resonances would mess with that though, but assuming that it's a real completeness relation, it should work. That would be a good question for a spectroscopy expert, perhaps. All right, so how much of the proton's mass is this green term, the quark masses? There's a very common claim. You'll see this in so many colloquiums, seminars. I think I've seen like some popular science news stories about it that will say that 1% of the proton mass comes from quark masses. And the way that you get this number is you sum up the masses of 2 up quarks and 1 down quark. But that's kind of misleading. The reason is we know from things like the phenomenology behind parton distributions that a proton doesn't consist of just 3 quarks. That describes its quantum numbers. That's its valence structure. The reality is that a proton is filled with this sea of quarks and antiquarks. It's constantly fluctuating. It doesn't have a definite number of quarks and antiquarks. But if you take the average of this operator, the average of this MQQ Q bar Q, then you get something very different than 1%. You have some probability of all the anti-up and down and anti-down, strange, charm, all contributing to this operator. And the truth is, there's actually a pretty wide margin of what it could be, somewhere perhaps between 8 and 20%. There are various reasons this is so uncertain. One of them is that we actually don't know this operator to great precision. There is some tension between lattice calculations of it and phenomenological extractions. And it also, And well, yeah, that's kind of it. Yes,
How many like standard deviations does that interval like?
I do not know. The best person to actually ask about the details of this, the technical term for it is the sigma term, would probably be Pia. I don't see her here today, but Pia is our local expert on the sigma term. So when you see her, you can ask her for more details about that. But the best estimates we have are from Lattice, I think, although they are a little bit in tension with phenomenology. All right, so one of the controversies, and this is actually a really hot topic, and I might get myself into some hot water by commenting on it, but there's the question of whether the gluon energy can be broken down into a classical part and a quantum anomalous part. So the first thing we need to get into is what we mean by anomalous. There's this thing called the trace anomaly or the conformal anomaly in gauge theories. You have that this energy momentum tensor, the gluon contribution to it, is classically traceless. If you take the trace of it, you contract mu and nu here, then your eta here, which I use for the Minkowski tensor, you just get a 4/4. This is alpha beta. This would be mu nu, mu rho, rho mu. So you kind of have a reverse happening here. So you get a relative minus sign when you swap around the indices, and you would get 0. So you have this gluon energy momentum tensor that is classically traceless. It's not actually traceless in the quantum theory. And the reason it's not traceless is because of subtleties to do with ultraviolet divergences and the need to renormalize the theory. There are a lot of difficulties with quantum chromodynamics that limit your choices for possible regularization and renormalization schemes. And by far the most popular one is dimensional regularization. Strictly speaking, you work in something like an infinite dimensional space-time without a manifold structure, and you define this D as the thing you get when you contract metric tensors with each other. Some people informally say you're working in 4 - 2 epsilon dimensions, although strictly speaking, that doesn't actually make sense. But that's just kind of an informal way of speaking. But you have this quantity D that you set to 4 - 2 epsilon. And a lot of formulas you can derive that depend on the dimension of your space-time. You substitute in 4 - 2 epsilon, and you expand out the quantities in a series in epsilon. And all of your ultraviolet divergence appear as 1/epsilon poles. So the idea here is to gather all your 1/epsilon poles, and everything else that remains, you take the epsilon to 0 limit. That's your answer. The 1/epsilon poles, they're pathological, you drop them. So you have a 1/epsilon pole here in your f² term. So you take this, you do your trace as normal, you get a D/4 here, because D is formally what you're treating your space-time dimension as. So you get a D - 4/4, you get a -epsilon/2 times this, which has an ultraviolet divergence in it. You get an epsilon/epsilon. You're left with something that is constant and non-zero, even in the epsilon going to 0 limit. So you end up with a trace in your energy momentum tensor in the quantum theory that you didn't in the classical theory. So this is pretty peculiar, but it's well known to be true, and it is believed to be intimately related to the emergence of mass in QCD. Now, at a formal level, without the trace anomaly, our proton would not be so massive. So in a way, it's related to the mass of the proton. That doesn't necessarily mean that your energy budget consists of a part that's anomalous and a part that's non-anomalous. So you have to ask the question then, can the gluonic contribution to the energy be written in a way like this, where you have a classical looking E² + B² term like you would expect from the Maxwell energy tensor, plus an extra anomalous part, or is this E anomaly term 0? Of course, there is the complication still that our field theory has ultraviolet divergences, we need to renormalize. And that's actually what this bracket with an R means. The bracket with an R means we've renormalized it. We subtract off any 1 over epsilon poles. So to address this question, we basically do the same thing that we did in the last slide. We identify and subtract any 1 over epsilon divergences. Now, to be mathematically consistent, we need to be very careful. We are not allowed to either remove 1 over epsilon poles or set epsilon to 0 until the very end of the calculation, after we've multiplied everything out. Yes.
Does that mean that you have to renormalize? So you calculate like E squared and B squared like totally separately, and then at the total end, so let's say there's two like totally equal and opposite, UV divergences in there. You allow them to cancel, and then only the other anything that doesn't cancel the next final point. Clear.
So you're talking about separating E squared and B squared?
Yeah. So you wouldn't want.
So technically, there actually is a rule that you are allowed to distribute this bracket over finite addition. It's provable that it doesn't make a difference.
Okay, got you.
Where you have to be careful involves multiplication. You can't distribute it. Say if you have a renormalization bracket of A times B, you can't distribute it as renormalized A times renormalized B, because you might have a 1 over epsilon in A and an epsilon in B, and then you would get rid of something that's actually finite. That's a good question. I probably should have cited John Collins's book on renormalization, because he derives and describes all of the rules for what you're allowed to do and what you're not allowed to do. It's a little bit of a difficult read. Collins is, in a certain sense, not very didactic or friendly in his writing, but he's very thorough. So he's definitely his books are definitely worth keeping as references for that reason. All right, so we want to write this in terms of the E and B fields. So first we need to clarify what the E and B fields are in terms of the field strength tensor. In 4 space-time dimensions, that's pretty clear. The 0 i's are our E's, and in fact that generalizes to any number of dimensions. And the ones where the I and J, the mu and u, are both spatial indices are your magnetic fields. That also generalizes. The one thing that's a little bit different is in 3 spatial dimensions, you can kind of get away with pretending your magnetic field is a vector field because it has 3 components. But it was never really a vector field to begin with. I mean, it doesn't flip sign when you do a parity transformation. It's actually something called a 2-form field. And in a general number of space-time dimensions, you have to keep the 2 indices. In any case, though, a sum over all i's and j's, if you're kind of double counting and you're contracting both the i's and j's together, you have to have a 1/2 to get rid of the double counting. But the idea is the same. If you have, here I'm going to go through this, replace your Greek indices by zeros and Latin indices. This is going to be a sum over your electric fields. Strictly speaking, you have to swap this so you get a minus sign, but then you move the I so you get another minus sign. Here you just move the I so you get a minus sign. And here you're double counting by summing over both of the indices, so you have to pull a 1/2 through as well. And what you'll get is an E squared minus a 1/2 E squared plus a B squared. So far, these are still our divergent quantities. We haven't applied a renormalization bracket, and we get that. And this is true of the regularized theory. You just apply a renormalization bracket, and that's it. Actually, I should have waited to have this appear until I got to this step. You were spoiled on the ending. So that's it. There's no anomalous energy. There's no extra E sub anomaly appearing here. Now, I do have to tell you that it is claimed by a lot of people that there is an extra anomalous term, and I believe that this comes about from basically a mistake that people make when applying renormalization and applying the rules inconsistently. So the derivations where people get an anomalous energy aren't given in enough detail to know that this is actually the mistake that's made, but this is kind of my reenactment or reimagining how such a mistake can occur. So you start with this operator, the gluonic energy. This is a agreed upon starting point. You then break it into a traceless part and a traceful part. So literally all I'm doing is adding and subtracting a 1 over d times this thing. So here's a 1/4. Well, you're 1/4 minus 1 over d and a plus 1 over d here. If you take the trace of this part, or rather if you replace the zeros with mu and nu and then took the trace, this would be traceless, this would be traceful, this would be the part that gives you the trace anomaly. And then kind of conceptually at this point, you might jump ahead and say, aha, this part has the anomalous energy and this is the non-anomalous part. And in fact, by going forward a few steps, we can even get that mistaken answer. So we again break into a 0 index and a sum over only Latin indices, which we can rewrite as chromoelectric and chromomagnetic fields. Here we have, because we had this 1 over d in this case, a 1 minus 2 over d. This isn't 1 minus 1/2, a 2 over d instead of a 1/2. And we have our finite piece that becomes our trace anomaly. So we can expand this to order epsilon by just doing the Taylor series expansion of 1 over 4 minus 2 epsilon. And then remember, we're not allowed to distribute the renormalization bracket over multiplication. But let's say we did that anyway. Then we drop this because it's order epsilon, drop this because it's order epsilon, and we get a 1/2 e squared plus b squared and this anomalous energy term. So we get a completely different answer than we did a few slides ago. But I kind of already spoiled what the mistake is. It's to drop these e factors here. And the reason that we can't do it is because the e squared and b squared terms have 1 over epsilon divergences. So we need to multiply them out. We could formally write EC squared as a kind of make up a term, a sub minus 1 over epsilon plus an a sub 0, and do something similar for b squared. But instead, what we can do is we can kind of gather our order epsilon terms together. Here's our 1/2 from before, our classical expression. Our b squared minus e squared, we could actually work backwards and say, oh, well, this is just our 1/2 of the f squared term. This is true in any number of dimensions. And we remember that f squared is going to give us our c over epsilon plus a finite. This 2 is from the 1/2 here. Well, now we have c, ooh, I should have removed that epsilon over 4, another typo. We have a c over 8 and a c over 8 that cancel each other out. So if we are careful about not distributing the renormalization bracket over multiplication, then we don't get the anomalous energy term. So in light of that, I think that a 3-term decomposition is the most sensible way to talk about the breakdown of proton mass into quark and gluon contributions. You have a quark mass contribution, a gluon kinetic energy, and a quark kinetic energy, sorry, and a gluon kinetic energy. And using some estimates that I believe came from a mix of lattice and phenomenology, these estimates come from this PRD by Andreas Metz, Barbara Pasquini, Simone Rodini. Very good paper, worth reading. They outline a bunch of scenarios based off of different existing phenomenology and lattice estimates. And using one of their scenarios, this is a possible breakdown of the energy. 2 things to bear in mind here. One of them is that the numbers are very uncertain. Another is that the separation between the quark blue part and the gluon purple part is renormalization scale and scheme dependent. The only thing that's scheme and scale independent is the quark mass, but there's big uncertainty. Moreover, the quark mass part cannot be written in terms of just mechanical form factors. However, the separation between quark and gluon, so blue plus green for quark, can be written in terms of mechanical form factors in terms of A and C bar. The gluon A and C bar as well, but with a sub G for the gluon contribution. And of course, since this is scheme and scale dependent, these form factors are also scheme and scale dependent. Anyway, that's what I have for mass, and I think I'm actually at about the end of this lecture, so I think it would be a good time for a break.
Is there any question? No?
Uh, my question is, why do you use dimensional regularization? Because we are dealing with a non-perturbative proton.
So dimensional regularization is by far the most common regularization scheme to use with QCD. Other regularization schemes that are popular for other field theories lead to problems with gauge invariance. For instance, in QED, it's common to give the photon a small mass. Well, that's more for infrared regularization. Pauli-Villers is another regularization scheme, but Pauli-Villers leads to problems with gauge invariance in QCD.
I know it is commonly used in perturbative theory, but I mean, could you justify why in proton system we could still use this regularization?
Why wouldn't you?
So you mean you could expand the operator in terms of different dimension? Is that what you mean?
As a series in epsilon? Yeah,
Okay, thank you.
this is pretty standard in hadron physics. It's used, for instance, in the defining of GPDs, parton distribution functions, and so on.
Wonderful talk, thank you. The constant that disappears when you take when we're looking at the total energy and we're looking at the anonymous contribution. Does that depend on the renormalization scheme? Like, are we in MS bar, or is that completely independent of normalization?
So that's actually a really good question. Because of the difficulty of using other regularization and renormalization schemes, this unfortunately hasn't really been explored much outside of dimensional regularization. A colleague of mine has talked about a work they're working on exploring another regularization scheme they found actually works for QCD, and also found that there isn't an anomalous part to it. But I shouldn't really comment on that at all since their work hasn't appeared yet. Actually, I'm kind of disappointed it hasn't yet. I've been eagerly looking forward to reading it. Something I've been meaning to do, and I'm actually kind of surprised no one else has done it yet. QCD, it's a problem to use other regularization schemes. But for QED, you can use Pauli-Villers. And QED also has a trace anomaly. So in principle, you could address the same question in QED using other regularization schemes. So I'm not aware that anyone's done that in QED, and I'm not really sure why. Another difficulty might have to do with actually creating a formal system of rules that you can provably follow or that you provably cannot use when you're using subtraction schemes other than MS or MS bar. So there are this collection of strict rules about the manipulations you're allowed to do with the renormalization bracket when you're working in what are called MS-like schemes, which includes MS bar and MS. But you need to have, your scheme needs to be mathematically well-defined enough in order to derive those rules. And that might be trickier for other renormalization schemes and other regularization schemes. Like with Pauli-Villers, I'm not sure how you would actually derive the rules for what you'd be allowed to do with the renormalization bracket. That might be a reason that this hasn't been explored in that scheme. But that is a good question. But hopefully in the near future, we'll see this explored with other regularization and renormalization schemes.
Yeah, is it possible to use this to like analytically compute the proton mass, just like from, you know, first principles? And does it?
No, I'm afraid not.
Gotcha.
We know analytically that the expansion has to have a 1 over epsilon pole for UV divergences. In principle, you could get over epsilon squared for infrared divergences, which is pretty nasty, but it is provable as well that if you account for everything consistently at a fixed order, the infrared poles actually cancel out. But a priori, I think, as far as analytical, well, maybe analytical is the wrong word. As for computing the coefficients that appear, well, Lattice doesn't use dimensional regularization. Lattice uses some other scheme that, or they have a collection of schemes. I don't really know much about Lattice, so I can't comment on that. But yeah, we don't have any reliable way of computing what those numbers multiplying the powers of epsilon are in first principles.
Okay, let's thank Alan again.